The BritChips Podcast is proudly sponsored by Silicon Catalyst UK.
What we're doing differently is we're not keeping it internal. We're making it available to developers from day zero so that they don't have to wait for the silicon to come out. They can actually run their models on the simulator and know how the hardware will look when it eventually comes out.
Hello, I'm Anthony Miller, and welcome to the BritChips Podcast, where I have conversations with movers and shakers in the UK semiconductor startup scene. Now, that was Kauser Johar, one of the founders of UK semiconductor startup Chipletti, and he was talking about a new simulator they have just released to the market. And the reason that this is exciting news is because it signals a significant pivot for Chipletti's business into the wonderful world of physical AI. Now, I first spoke to Kauser and his co-founder Catriona Wright in the BritChips podcast back in June last year. Chipletti, you may recall, was one of the startups selected to participate in the third cohort of the government-sponsored ChipStart incubator managed by Silicon Catalyst UK. And at that time, they were hard at work developing high-speed cache memory chiplets, the clue is in the company name, designed to stack on top of logic chips so you get more cache memory without needing extra space on the silicon. But that's all changed, as you will hear right now. Kauser, Catriona, welcome back to the BritChips podcast. So, Kauser, tell us, what's changed?
Yes, so a lot has changed, but fundamentally, the principle of we wanting to stack memory hadn't. So when we spoke last June, we had to then do detailed work on the design of the memory chiplet and actually try and quantify how much performance our potential partners would get. So we set out over the 6 months after that to do detailed benchmarking, simulation work to understand for different applications how much performance improvements you can get by stacking memories. And we were pleasantly surprised. So we have basically taken all of those learnings from the last 6 months of the project work.
Okay, because this was, I said, you were working really just on speeding up cache memory, basically, or rather reducing the footprint for cache memory. But now it seems like you're moving into edge AI. Can you kind of build the bridge between what you were doing and what you're now doing?
Yes, so cache memory was one option, but in terms of application, we were specifically focusing on AI inference, not AI training, model training, but AI inference as an application. Now, the simple conclusion of the work we've done is stacking memory have mechanical and thermal challenges. So heat needs to dissipate from the chips vertically upwards typically, and the best possible power range for stacking chips is not the hundreds of watts in data centers. It turns out that it is at a lower point, so around 10 to 15 watts. So that really focused our approach to focus on applications which are in the 10 to 15 watt range rather than hundreds of watts.
And what sort of applications would those be?
In short, applications like AI, where AI is deployed in battery operated devices, but with a larger battery capacity. So not your Ring doorbell, your Alexa always on, but rather things like drones and robots, cars. So they have more power budget than your mobile phone, but at the same time, they're not rack mounted in a data center.
So they're self-powered and they're mobile is what I'm getting.
Exactly. And at the same time, they have more power budget compared to your mobile phone. So drones and robots operate at a higher power point.
Right.
Additionally, it's worth clarifying that the architecture that we were designing on how we would organize the memory,
Yeah.
it turns out that real-time applications, so deploying AI models on real-time applications, and I say robotic applications, drone applications, cars, they are real-time applications because you can't wait for an answer. You have a fixed time by which you need an answer and then act on that answer. So our architecture was more suitable for real-time applications.
So it's like image recognition, for example, in a robot or some similar device. Obviously, if it spots something and doesn't recognize it, you want it to be able to recognize it in double quick time in case it's something dangerous or whatever. Is that what it is? It's a latency issue.
Exactly. So uh, typically people use GPUs for that, and GPUs are fast. They are power hungry, but they're fast, but they're not exactly fast all the time. The majority of the times they'll be fast, but sometimes because the way the GPU interacts with memory, it might miss the time budget. So imagine your robot is working as it's expected all pretty much most of the times, but there's this one instance where it misbehaves. That can have lethal consequences.
That could have
So
disastrous consequences.
exactly right. So imagine if you're deploying GPUs on a data center running large language models. If sometimes you have to retry, that's okay, but you can't retry in a real time environment. And that's fundamentally the mission we have, which is designing an architecture which is optimized for such applications. And you're not retrofitting a GPU and taking it to deploy on a real time application.
So what I think I'm hearing is that your new design is going to be more resilient, more reliable because it's designed for these sorts of applications and also consume substantially less power than a traditional GPU. Did I get that kind of right?
Perfect.
Okay, good. Got that bit. So you're still going to be designing chips though, chiplets, I should say. But these are chiplets specifically designed for AI inferencing in the sort of, you call them physicals of edge AI applications. It's still
Yes.
chiplets, yeah.
Yeah. So
Okay.
we're still at the heart taking a chiplet approach
Yes.
and a vertical stacking approach. So chiplets can be integrated in many forms, but we are designing chiplets that could be vertically stacked on top of each other. The thing that has changed from last year is initially we started off just designing memory chiplets. Now we are designing the compute part as well, and we would integrate it ourselves. So previously we would have sold the memory chiplets to our partners, and they would have done the vertical integration. Now we would design the compute chiplet and then do the integration, package it up. And what our new customers who are designing robots and drones would buy is the full package part, or even a module that you can connect to like a Raspberry Pi and get up and running.
Well, that's a really significant advance in what you're doing. So no longer just the memory chips. Now you're going to do the compute chips. You've got to integrate them and package them in a way that is appropriate for the customer. I mean, that's a big change, isn't it?
It is. And as I said earlier, it was as a result of the work we had done over the 6 months after we spoke to you initially and the results we saw in our simulation. We were like, well, we want to accelerate the deployment of that ourselves.
Well, let's talk about the simulation because that's, I guess, the other big news that you've got, that you do now have a simulator that I assume can sort of model this new step forward, both the memory and the compute chips. How long did it take you to develop the simulator?
So we've hired a really great intern who's doing PhD in Cambridge University. And so us, along with the intern, we've been working on it for a few months at least, mostly at the start of this year, some background work at the back end of last year. And we have reached the first stage where we can actually roll it out to our potential customers and partners. Now, obviously, work doesn't stop here, and there's still a lot of work that continues to happen in the background. But we have reached the first stage where we can showcase the performance of our eventual system that would be in silicon in the simulator.
And have you shown that to any customers yet, or potential customers or partners yet?
Yes, so that's the work that has started now. There's a list of people we have been closely collaborating and working with. And over the next few weeks, we will be working with them so that they can then try their AI models, deploy it onto our simulator, get numbers, and then take the conversations forward. But at the same time, we have also made the simulator available to everyone. And this was the announcement we made last week, which was we want to do development very differently. People, I mean, who designs hardware typically also builds simulators to understand how the hardware will perform. And that's a standard practice. So we're not doing anything new there. What we're doing differently is We're not keeping it internal. We're making it available to developers from day zero so that they don't have to wait for the silicon to come out. They can actually run their models on the simulator and know how the hardware will look when it eventually comes out. And if they want to tweak the model, then and learn from what new hardware will be available in the future. And that's a big gap we see in the market today, where people who are designing models can only test and validate them on hardware that are available today. But there's a lot of hardware development that's happening that will come out in 2, 3 years' time, and there is no real way for people to test how their model will behave then. So we want to make the simulator available now from day zero.
Well, I must admit, so this is perhaps a little above my pay grade because I struggle to understand how you develop a simulator to model hardware that doesn't yet exist because you don't know the characteristics of the hardware, surely.
We do. So we have each individual pieces of components in the chip, whether it's the memory and how the memory is laid out, whether it's the compute and the instructions and the tool chain that compiles models onto that instructions. All of the individual pieces of IP, they are very well characterized. So we know how the memory behaves, at what frequency you can run at. We know what the compute is, how what frequency it runs at, how many cycles it takes to execute certain instructions, and then we abstract that away with high level software. So these are not transistor level. This in the simulator is abstracted at a high level software. And then all of these pieces are put together, and they don't run as fast as the hardware. So the hardware will run at gigahertz. The simulator runs at kilohertz.
Yeah.
So orders of magnitude off. But it's also not completely cycle accurate. So it will not tell you 100% correctly that this is how it will behave, but almost accurately, because these are very well correlated with the real hardware.
The customer has a very high degree of confidence that the output from the simulator will be pretty close to what they might expect. And if I understood what you also just said about how you're predicting future technologies, what I now understand is that in your simulator you can say, well, supposing we have a memory technology that works 20% faster, what impact would that have? If you have a CPU chip which runs at twice the speed or whatever, you can model that at all, even though that hardware may not physically exist yet, so that they can
Exactly.
then say, well, okay, here's where we are. We should design it now with what we've got, or maybe we just wait a little longer till the new technology is out. It gives the customer the opportunity to look forward rather than just look at the present, if you want to put it that way.
And that's fundamentally the problem we see today, which is people who are actually designing models, they're not necessarily designing models for today's application and today's hardware. They want to be forward looking.
Yeah.
And there is no way for them to have the detailed understanding of what tweaks you're making at the transistor level or what will
Yeah.
happen at the process node level. And so, from their perspective, is my model going to be better, worse, different in the future hardware? There is no way for them to know.
No, absolutely. And given the length of time it takes to actually manufacture silicon once you've got the design, you can be months away. But can I just understand and make sure I haven't truly missed the point here? Does your simulator only simulate for chipletties design, memory design? Chiplet is chiplets, basically, your memory chiplets and your CPU chiplets.
The detailed work on all of the individual pieces of components we have done, we have created, abstracted that away, put them together in a simulator. So
Yeah.
it is modeling our system and how
Right.
our system will behave for those models rather than any generic hardware. We have ability to tweak the simulator to model different hardware, but we use that for internal research on how our hardware will compare with other hardware in terms of optimizing our offering. But from our partners and developers' perspective, what they get access to is our system and our simulator.
Because do you charge for use of the simulator?
Yeah.
Okay, so it's basically a marketing tool to help your potential customers understand really why they should go ahead and invest in your chiplets. You said you've got two partners kind of looking at this now. At what point do you think they'll say to you, Catriona, Kauser, this looks great. We'd now like to order some chiplets.
Yeah. So you touched upon earlier in the conversation that it takes a while to build silicon. it takes a lot of capital to build silicon. So before we put all of that investment to commit to building 3D stack chips, we will phase our development. So the first milestone was to make the simulator available to our partners. The next big milestone, there are smaller milestones in between, but the next big milestone is to actually deploy all of the IPs onto a FPGA and create a module, a PCB module, which is the size of uh, um, you can fit it under your palm, integrated with, for example, Raspberry Pi. So what we didn't touch upon was our mission is to make deployment of these models simple, fast, and predictable. So we
That's what
don't
FPGAs allow you to do, the field programmable gate arrays, because they're sort of industry standard devices, aren't they, which you can program and reprogram to suit, to fit in, according
exactly.
to your design. When would you hope to have an FPGA version ready for demonstration?
So our plan is to have that ready by the end of this year.
End of this year. That's fantastic. And you said that was a sort of step in between. Sorry, was that the step in between, or was that the next major big step?
So that's both the step in between to get to silicon and also the next major step.
Okay, because the step after that then is to go to the silicon.
Yes.
And, in your dreams, so to speak, when would you hope that would happen?
So our plans are quite aggressive. Our current plan is to tape out, which is the process
Yes.
of sending finished designs to the foundry for manufacturing around the second half to the back end of next year. And it can take around 3 to 4 months after that to get the first samples back. So if things, if all the stars align, then we could have first silicon towards the end of next year or the beginning of the following year.
So these are quite significant steps, obviously going to FPGA and then going to tape out. What extra funding do you need to get to these milestones?
Always the question comes back to funding.
It's always the money question.
Yeah. So we're currently raising our pre-seed round. We're looking for 1 million, which will carry us through for a year and allow us to grow the team. We want to get 6 more people on board so that we can develop the simulator further, as well as do the FPGA that Kauser was just talking about there. In terms of how we're getting that, we've had some interest from angels. We're currently looking for a lead VC. We've also applied for an Innovate UK grant. I'm not sure if you've heard about the semiconductor and components for smart electronic platforms, I think is the full title. So we should hear about that next month. So yes, we're seeking funding from different sources, as is the way.
And if everything goes smoothly, when would you hope to be able to get that funding in so you can actually proceed to the next milestone?
I mean, the simple answer is as soon as possible.
As
we want to
possible.
grow the team. Yeah, we want to grow the team. So we want to get people in the door as quickly as possible. But, ideally, if we can sort this out in the next couple of months, then we've got enough time to meet our roadmap.
So the team currently is you two, and you mentioned the intern who's done the simulator. Is there anybody else working with you on the team currently?
We've still got our advisor from Chipstart. He's keeping in contact with us, and he's a brilliant person to go to for networking and just brainstorming with. He's fantastic.
Do you want to give him a name check?
Steve Evans, yeah.
Right. And so you're still very, very much involved with Chipstart, at least through the mentor. Are they able to help you with the pre-seed funding round?
So they put us in touch with a few VCs. We went through talking to lots of VCs last year, so we're reconnecting with them. With the extended network, as it always seems to be the way it works, we're being introduced to new VCs as well. So there's lots of conversations going on at the moment.
Because it sounds really exciting what you're doing. I am aware, I speak to many other startups, both in Chipstart and outside of Chipstart, who are working on variations of, I guess, AI accelerators in some shape or form. And this sounds like it's a very exciting and a very wide open market, because I don't think I don't think there's any chance there's going to be a dominant player, certainly at this early stage. But how would you see your technology kind of matching up against the others that you might be aware of that are also trying to basically optimize edge AI, if you want to put it that way, to reduce the power consumption, increase the operating speed? Where do you think you fit into that?
Our belief is that AI inference in general, whether it's edge or data centers, it doesn't matter, is a memory bandwidth problem and not necessarily a compute problem. So there are a lot of people who are tackling this scale of the problem by designing either a new instruction set, architecture, new compute, either doing analog compute or using photonics. There were a lot of news around photonics recently. But fundamentally, the cost, the energy cost or the power cost comes down from moving data around from memory into compute. Um, and that is the problem we set out to solve, which is how can we bring the memory as close to compute as possible via the 3D stacking. And so that is how we differentiate ourselves from others. And then what we learned was that the other problem that the people are facing is that quite a lot of the compute being designed today actually is quite efficient and fast when they run a specific AI model. Um, we had the wave of deep neural networks and machine learning models in the previous decade, and then the arrival of large language models, transformer-based models post ChatGPT. People are exploring new models of very different types. So we don't want to end up in a fragmented situation where you end up with a hardware that can run one type of model very fast, but actually what is required in applications is, for example, sensor fusion, where you're taking inputs from different sensors and you're using different models. So our focus was to make the compute very generic that can actually adapt and run different models, but fundamentally tackling the same problem, which is memory bandwidth.
And your design will allow that running of different models, so it's not fixed to it's not set for a particular model. It's going to be flexible enough to be used with different implementations.
Yes.
But also, it sounds like, as you said, and this was, I think, the really significant, or one of the really significant parts of your new development, is that you are also designing the core logic chip to work in conjunction with a memory chiplet, so you get this very tight level of integration, which just having an accelerator just for the CPU or some sort of memory improvement technology is only kind of half the story. What you're going to be presenting to the market is, if you like, the complete solution, the low power, low latency, high performance for those sort of physical AI applications, isn't? And I don't think I know of anyone else who's doing it in quite that integrated fashion.
Yes, and I think one point I would add to that is all those metrics matter, but there's an additional metric that matters, which people don't talk about, is the predictability. And so the way we organize our memory, this is the patents we filed a couple of months ago, was on how we make the execution of the models predictable, because it matters in the applications we are targeting.
Have you had any potential customers show interest in your technology?
So the interest so far we have had from is people working in the defense. And the reason why that is interesting to us is because people are talking about sovereignty, even in defense, trying to build resilience of the supply chain and being able to build a full defense capability completely sovereign, in a sovereign way. Now, pretty much everyone is, they're focusing on the software, they're focusing on actual systems and beyond that, but no one is actually talking about where do you build the chips and who builds the chips and where do you get the chips from. And one of the things that people found attractive from our solution was that we don't need to use the Taiwanese fabs or the Korean fabs because we're using a mature process technology. So everyone is trying to chase the greatest and shiniest process node from TSMC and Samsung. We get our performance by vertically stacking on a mature process node, so we can build more closer to home.
It also makes the point that you're really building something which kind of bolts on to their hardware, isn't it?
Yeah.
Your chiplets will clip on, so they're not having to do a complete redesign to use your stuff. They can, solder it on, so to speak, to their
Yes.
existing. Yeah, well, I mean that's huge. I mean that really is huge.
I mean, I think for me, it is the focus on physical AI and what a massive market it's going to be. And it's only just starting. I mean, everybody is, whenever they think about AI, they think about data centers and AI agents, whereas physical AI is still in its infancy. And there's so much potential for where it could go. We need to get in early with the hardware, particularly, so that we can support all the things that people are going to come up with, ideas that today we haven't thought about yet, that can still do that, because that hardware takes a long time. So we've got to be ahead of the game and make sure that we've got the performance in place for the people that are writing the models to be able to implement later on.
That's great to hear the progress that you're making. So, Catriona, Wright, Kauser, Johar, thank you very much for joining me yet again on the BritChips podcast.
Thanks, Anthony.
Thanks, Ed.
Love speaking to you always.